Hey guys, welcome back to another series and another video. In this new series, we are going to be solving some of the hard questions from organic chemistry, that is from AS level chemistry, and we're going to be solving the MCQs from it. Right, so let's start off with the first question, and it is from March 22. Okay, variant 2. So the first question is, compound Y is heated with a mild oxidizing agent. One of the products of this reaction, meaning after you have oxidized Y, that is, you have oxidized Y, you get a product. Okay. Now, one of the products, this product of the reaction, reacts with hydrogen cyanide. So let's say this product reacts with hydrogen cyanide. Okay. Forming 2-hydroxybutene-nitrile. Okay. After the reaction has taken place between the product of the first reaction and hydrogen cyanide, what do we get? We get 2-hydroxybutene-nitrile, right? 2-hydroxybutene-nitrile. Okay. So is it a butane? Yes. 1, 2, 3, 4. Yes, it's a butane. And is it a nitrile? Yes, there's a nitrile group over there. So that is your product after you react the product of initial reaction and hydrogen cyanide. So this is what you get. Now they're asking, what is compound Y? What is the compound that you start off with? Great. So how do you solve these type of questions? You have to backtrack. You have to start from the end. How do you do that? First, you have to figure out what X is, meaning, you know, the product is butane-nitrile. So your reactant has to be some sort of aldehyde. Why? Why does it have to be some sort of aldehyde? Because you're reacting with hydrogen cyanide. And when you react when you react aldehyde with hydrogen cyanide, what happens? Addition reaction happens. Nucleophilic addition. What is the nucleophile? The CN group. The CN group is a nucleophile, and that is going to break the double bond of the aldehyde and form a nitrile. So, from studying, you must have already come across the reaction of addition. I mean, the nucleophilic addition reaction, where the end product is a nitrile. Formation of nitrile can be done by reacting aldehyde and hydrogen cyanide. Okay, so now you know X is what? An aldehyde. Great. So if X is an aldehyde, what aldehyde is it? Now remember, when addition reaction takes place, there is a carbon atom added from the cyanide group. The cyanide group has a carbon atom attached to it already. So the aldehyde that it reacts with, number of carbon atom it has, it's going to add another carbon atom and form a nitrile. Therefore, the aldehyde must have one less carbon atom. In that case, what will the aldehyde be? Very simple. It's going to be this, right? It's going to be a propanol. 1, 2, 3. We have a propanol. After the propanol reacts with hydrogen cyanide, a carbon atom attaches, and you have butane-nitrile. Okay. Now, it's going to be an aldehyde again because it could have been a ketone. It could have been a ketone as well, but you know the cyanide group, the nitrile group is at the end. Therefore, you have to have an aldehyde or work with an aldehyde so that the nitrile group can be added at the end, right? Great. So when you're reacting with the aldehyde, what's happening is the nucleophile comes in and attacks the carbon attached to the oxygen, and it's going to this negative charge is going to repel the double bond, the electrons in the double bond, and it's going to make sure the pair of electron goes to the oxygen atom, and it removes the double bond and puts a single bond over there between oxygen and carbon atom. And in that case, what happens is the oxygen will have a negative charge, and it's going to attract a hydrogen, and it's going to form an OH bond. And this part, it's going to remove the CN nucleophile is going to remove this hydrogen atom, it's going to push it away, and it's going to form OH, and this is what it's going to form. So how the OH, again, it's going to put a single bond between the oxygen and the carbon atom, and then since the oxygen atom has a negative charge, it's going to attract the hydrogen ion, positive hydrogen ion, and it's going to form an OH bond, and between the CH bond, the CN is going to push it away and it's going to break off, and in that position we are going to have a nitrile group. Okay, so that's how this reaction 2 is happening. So now you know what X is. X is a propanol. Okay, so if X is a propanol, that means you know the end product over here, which is a propanol. Now, you know Y is being oxidized to form a propanol, which is X. So in that case, what could Y be? What can you oxidize to form aldehyde? Simple, a sort of alcohol, right? So now you know you're oxidizing an alcohol to form X. Now, what could that alcohol be? You can already cancel out butanol and butanol. Why? Because you don't have 4 carbon atoms, you have 3 carbon atoms to work with. Because it's a propanol, 3 carbon atoms. So cancel off A and B. Now you're left with 2 options, propan 1-ol or propan 2-ol. How are you going to decide that? Very simple. Since the double bond is at the end, that means the OH functional group must have been at the end as well, or else it couldn't have been oxidized at the end and formed a OC double bond, right? So therefore, it must have been this alcohol, which is propan 1-ol. If it would be over here, the double bond would form over here as well. Therefore, your Y must be propan 1-ol. That is your alcohol. This was a pretty good question. Okay, so that's why your answer is C. Great. That is question 1. Okay. Then moving on to question 2, what do we have? We're going to do this 26. That is from Australia to variant 1-2. Okay, in this question, alkenes and cyclic alkenes should be considered. How many structural isomers of C4H8 are there? Okay, so it's the question from isomers. Now, how do you deal with these type of questions? First of all, let's start off with molecules, or I mean the discrete formulas with no branch, right? Without any sort of branch, and with just, is this an alkene? In this question, alkenes and cyclic. Oh, right. So these are all alkenes. And C4H8 can only be alkenes or cyclic alkenes, because in case of alkenes, it should have been C4H10. Okay. So these are alkenes or alkenes, and you should start off with the molecules which are not branched. You can start off with the cyclic ones as well, your choice. But yeah, I'm going to start off with the ones which are not branched, right? So in this case, what I'm going to do is, first of all, I'm going to change the double bond position. That's the simplest thing to do. So if you draw the 4 carbon atoms, you have the double bond in the first position, and that's giving you this molecule. And then you move the double bond to another position, and this is giving you this molecule. Now, can you change the position of the double bond to have any other different arrangement, any other different molecule? No. If you move the double bond over here, it's going to be the same thing as before, right? Okay. So in this case, now you're stuck with these 2. Now what you have to do is get into branches. Okay. Now if you branch this carbon atom out into position 2, what you're left with is this molecule, where you have a double bond at this end. Now, you might be thinking, why not move the double bond into these 1-2 position and have more 2 different molecules? But you can't do that. Why? Because if you, let's say, move this double bond, put a single bond over here and move the double bond over here, what's going to happen is, this is the exact same thing rotated in this manner. Therefore, this is the same thing as this, which is why changing the double bond in this case, where you have already branched the discrete formula, you cannot have different molecules. You won't have different molecules, which is why you're stuck with these 3 planar molecules. I mean, these are not cyclic by any means, right? So these are your non-cyclic compounds. Now, after you've saturated all the options, you move on to the cyclic compounds, right? You have now three options with branched and non-branched structural formulas, right? Now, if we go into the branched formulas, what's going to happen is you can have 3 carbon atom branched, and you can have all of the 4 carbon atoms as branched. If there were 5, you could do that for 5. If there were 6, you can do that for 6 as well. No problem. Okay, so if you have 3 of the carbon atoms in a cyclic form, you will have 1 methyl group as well hanging out there. So if you change the position of this methyl group, is it going to affect your structural formula? No, that's not going to affect your structural formula, since it's basically the same formula, just in different positions. And nothing is distinct about the CH3 being over here or over here. So it's the same formula, just in different, from different perspectives, right? So in that case, you're left with only 1 cyclic compound over here without any other change of position, right? So you have 3 plus 1, total 4 as of now. Now again, you can combine all of the carbon atoms and form another cyclic compound. And in this case, you're going to have 4 of the carbon atoms together, and you're going to form a cyclic compound, right? And in this case, can you change anything? No, you can't. You can't really change anything. So therefore, this is your final, your 5th structural formula. Okay, so these are all your structural isomers. And since they've only asked you to figure out from structural isomer, you cannot have any sort of... Could you have optical isomers over here? No. Okay. Yeah, no. Okay, so these are all your 5 isomers. So your answer is 5. Since you cannot have any less anymore, this is very simple. So your answer is C. You can have 5 structural isomers. Right. Okay, so now let's look at question 3. I mean, this is a pretty difficult one. It's interesting. Yeah, it's from polymerization. So let's look at the question. The diagram shows a section of addition polymer found or formed from 2 different monomers. One of the monomer is propene. So basically, the only clue they're giving is one of the monomers is propene, and you have to identify the other monomer. Now, why is it difficult? Because identifying the monomer from this heck of a complication is a mess. So I would suggest you do this at the end when you're not in panic, because this needs a lot of, concentration to figure out where the bond lies. It's like a puzzle. So the first thing you do is forget about the extension bond. In this polymer, you don't confuse yourself with the extension bond. These are the extension bond, meaning if this was your double bond, right? This was your monomer. The double bond would be erased, broken off, and you would have these extension bonds. These are not a part of your monomer, so forget about those. Now, they've given you a clue, which is one of the monomer is propene. So if it's a propene, what's going to happen is, that's a propane and this is a propene. If it's a propene, this double bond is broken off, and there's an extension bond over here and an extension bond over here, meaning this bond is going to connect to another monomer, and this bond is going to connect to another monomer. Now, do we have something similar to this? Yes, we do. If you look at this part, if I draw this like this, yeah. So this is exactly the same as the part over here. Notice so this part is actually your propene that has been polymerized, right? So this was your propene, where the double bond actually was over here. This was your double bond over here. Between 2 and 3, the double bond lied. And the extension bond came from over here and to over here. So therefore, you have to omit this part again. This is your extension bond. That is your extension bond, and this is your propene. Great. So if this is your extension bond, forget about that. What is the next monomer? How do you find the next monomer? Very simple. I'm basically going to find this same, the same shape after the first propene molecule. You're going to look for the same shape after the first propene molecule. That is the polymerized propene molecule, the monomer. The polymer. So where do you see the repetition after the first one? If I plug it in over here, is it a repetition? Is it a repetition? No, it's not, because there's a double bond over here. We don't have a double bond with R1. So where could it be? If I plug it in over here, no, there's no bond over there. Okay, if I plug it in over here, yes, this could work. Why? Because notice single bond, single bond, single bond, single bond. And our one had single bonds as well, especially because it's a polymer. But also notice in this polymerized part of the group, this has a double bond. How did that happen? Actually, that has a reason, and I'll talk about that reason a bit later. But before I delve into that reason, I need to clear out why that's the monomer. So notice that this repetition of the propene polymer is again coming after 1, 2, 3, 4 position. After you skip 4 position, you're going to see the same repetition as before without any double bond, because over here you didn't have any double bond, right? There was one repetition over here, but it was ruined by the double bond between 3 and 4. That's why we're not going to take it over there. Plus, if you considered it over here, then where is the other monomer coming in, right? So in that case, we skip to the next one. We don't find it. Again, we skip to the next one. Now we do find it. And over here, remember, this is your extension bond. This part is your extension. And which was the other one? This was your extension bond, right? So in this case, forget about this bond. Forget about this bond. This is your propene, right? And lying between this part and this part is another monomer, which is basically 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. That is your another polymerized version of the monomer, right? So what's happening over here is this polymer, if I try to draw the monomer out of this, it's going to look something like this. Most likely, the double bond is definitely going to be between 2 and 3, because there's an extension bond over here. And if it was over here, this wouldn't work out, because this end would need to be connected with this end. So the double bond needs to be between 2 and 3. If it was between 2 and 1, it wouldn't work out, right? Because the extension bond, from this point, there would have to be another extension bond as well. Okay, so over here, 2 and 3 must have had one double bond, and the other double bond is the other extension bond over here. This is your other extension bond, and this extension bond is directly connecting to the 5th carbon atom. Therefore, the double bond must have been over here. But the interesting thing is, why is there a double bond between 3 and 4? Now, if you notice, the right answer is actually D. Why? That is very simple, because in this long chain, 1, 2, 3, 4, 5, and 6, there's no branch, right? There's no branch, but in all of these 3 options, there's a branch. And we can simply omit ABC out of the equation just because they have these branches. Okay, so therefore your answer is actually D, because it's not branched. This is not branched. Therefore, your answer is D. But the problem over here is, why is there a double bond between 3 and 4, but there is no double bond between 3 and 4 in the monomer, right? What has happened is, when the polymerization was taking place, the double bond was broken between these 2 ends, and the double bond formed between 3 and 4. Why? Because otherwise the carbons would not have 4 bonds. The carbons would not have 4 bonds, which is why when these were broken off and extension bonds were made, a double bond needed to be made, extension bond over here and extension bond over here, right? So in that case, a double bond needed to be made over here so that all the carbon atoms have 4 bonds, right? Therefore, your answer is actually D. Okay, right. This was fairly complicated, and hopefully you're not going to have questions like this. If you want to see it again, the repetition of the propene, you can see it again over here. This is the propene. Sorry, this is the propene. This is the extension 1. Again, 1, 2, 3, 4, 5, and 6. Again, this ends with the second monomer, right? The polymerized version of the monomer. Okay, so that is your question 3, polymerization. All right, question 4. The structure of conine is shown. This is your conine molecule. And conine can be synthesized by reacting ammonia with dibromo compound X. Compound X is such a molecule that has 2 bromine atoms, right? What is the name of compound X? Okay, it's definitely going to have 2 bromo atoms, that's for sure. But the important part over here is when you react this compound X with NH3, what's going to happen is it's going to form this cyclic compound. Okay. Therefore, to work with this kind of question, what you need to do is find out a formula, a structural formula for X where a cyclic compound can be formed. What you need to do is find formula which can form cyclic compound. Okay. Now, the other thing is, how does NH3 react, right? How does NH3 react? So now you can also notice that as the product you have HBr. So if you can connect the dots and remember the substitution reactions, how NH3 reacts is basically it forms an amine group. It forms an amine group by having substituted the halo compound, the halogen, or any other form of group in the structural formula. That is, if you have C, and over here you have, let's say, Br, right? What's going to happen is your NH3 is going to come in, and the H is going to react with Br, and it's going to go away, and you're going to be left with C, and NH2. That is your substitution reaction with ammonia, right? So if we know that, we know we're forming 2 HBr molecules. So from that, you can assume that some sort of substitution reaction is actually taking place. Therefore, if some sort of substitution reaction is taking place, right now, this is the tricky part. You have to assume that both the hydrogen atoms of NH2 is actually reacting with both the Br atoms and forming HBr. And in doing so, nitrogen is forming a bond with carbon atoms, both of which are connected to the Br atom. How do we find that? Basically, we need to work with a long chain carbon molecule where you have the bromine in the first and on the 5th position. If you have the bromine in the 1st and 5th position, in that case, your NH3 can come in and have an attraction with the Br atoms. In that case, your H is going to react with the Br atom over here, and it's going to form a bond. This H is going to form a bond with this Br atom as well. And in doing so, this nitrogen is now going to form a bond with these carbon atoms, the 1st and 5th carbon atom, and it's going to join both of these together, being the 6th member of the cyclic compound. So you're going to be left with this NH, because both the hydrogen has reacted with bromine and has been given off as HBr, hydrogen bromide. Therefore, it needs to be this molecule where you have the bromine atom separated by 3 other carbon atoms. The reason these are not going to work is because your bromine atoms are not separated by 3 carbon atoms, and they're not going to connect to form a cyclic compound. So A and B is out of the equation. The reason 1,4-dibromooctane is not going to work is because in between 1 and 4 there is only two carbon atoms, which is why it's not going to connect and form a cyclic compound such as this. If this was not given, you couldn't have figured out between 1 and 4. Or honestly, you couldn't even have figured out between A and B. Right? So that is your question 4, where you're forming a cyclic compound by a substitution reaction where you're forming an amine group, right? How are you doing that? The H is forming a bond with the Br and is getting out of the solution. Reaction is being the product, and it's the nitrogen is actually forming a bond with the first and fifth carbon atom and joining the cyclic circle. Okay, so question 5. What is question 5 saying? Which reaction has a nucleophilic addition mechanism and gives a good yield of product under the stated conditions? Okay. So it needs to be a nucleophilic addition mechanism. So it can't be propane, it can't be iodopropane, because propanes are not going to have any sort of addition reaction. So A and B is out of the equation. Now you have propanol, propanol, reacting with hydrogen cyanide, HCN. Under alkaline condition, if you're reacting with HCN, therefore the nucleophile is actually CN, right? CN is your nucleophile and it's going to attack this carbon atom and it's going to push this away, and you're going to be left with C, 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 and C. You're going to be left with a nitrile group, right? Okay. You're going to be left with a nitrile group. Okay. So now the question is it going to be an alkaline condition or acidic condition? Notice that if it is an alkaline condition, you're going to have KCN, which is basically the CN nucleophile. Now, the reason you need the alkaline condition is due to the alkaline condition, you're going to separate the CN nucleophile and have it react with the what was the reacting propanol. The CN nucleophile is going to be able to attack the propanol compound. Otherwise, if it was acidic, what's going to happen is in acidic condition, HCN will not break off. In acidic condition, HCN is not going to break off and stay as a compound, and the CN cannot go ahead and attack the propanol molecule, right? So you need to have an alkaline condition to be able to have the nucleophile CN separated in a sense to be able to attack the propanol compound and carry out the reaction and have a greater yield, right? If it was acidic, there would be far less CN nucleophiles attacking the propanol compound. That is why your answer is C, and you need alkaline conditions. Okay. So this is it for this video. We've solved 5 questions and we're going to solve the rest in other videos.